So let's go ahead and look at some additional practice for Chapter 13. Number 1, titanium metal has a body-centered cubic unit cell. Okay, so I've got BCC. The density, D means density, the density of titanium is 4.50 grams per centimeter cubed. Calculate the edge length of the unit cell and titanium's atomic radius. Okay, so for edge length, I'm going to take the cubed root of the volume of the cell. Because it is a cube, I know that cubes, we'll pretend that actually looks like a square. Volume is equal to L cubed. So if I want to find the edge length, I need volume. I also know, because it's body-centered cubic, that L is equal to 4R over the square root of 3. So how am I going to do this? Well, let's see. My volume of my cell is equal to the mass of my cell divided by my density of my cell. What is the mass of my cell? I don't know. I'm going to find that out. What's the density of my cell? 4.50 grams per centimeter cubed. So let's go ahead and find our mass of our cell. I want to now find the number of grams per cell. I know that I've got titanium, so I look up titanium on the periodic table, and I see it's 47.87 grams of titanium per 1 mole of titanium. That's for 1 mole. I want 1 cell, or I want one atom then to 1 cell. I've got 1 mole of titanium, and I know 1 mole of titanium contains 6.022 times 10 to the 23rd titanium atoms. Now I could find the mass per atom, but I want it per cell. I've got body-centered, which means 2 atoms per cell. Remember, body-centered has 1 at each corner. And 1 in the body. So 2 atoms per cell. So I'm going to say times 2 atoms per cell. Or 1 unit cell. This gives me 3.53 times 10 to the minus 23rd centimeters cubed. Oops, I just wrote down the wrong unit because I was looking at the wrong thing on my page. I apologize. I should look at the right thing. 47.87 divided by 6.022 times 10 to the 23rd times 2 gives me the correct answer would be 1.5898. I'm going to underline the 9 there because my sig figs are at 4, but I don't want to round that right now. Grams per cell. Now I have the answer to put in the numerator here. 1.5898 grams per cell divided by my density, 4.50 grams per centimeter cubed. Now I find that my volume for my cell is 3.533 times 10 to the minus 23rd centimeters cubed. So I found my volume. I'm consumed by my edge length. I do have a second option here, though, to figure this out. The other way I could calculate that, let me write this down here. Option number 2. Number of centimeters cubed per cell. I know that I have 1 centimeter cubed to 4.50 grams. I know titanium is 47.87 grams of titanium to 1 mole of titanium. I know that 1 mole of titanium is 6.022 times 10 to the 23rd atoms of titanium. And I know it's 2 atoms per cell. So you could do this all in one fell swoop. I don't really care if you do it in one calculation or two. You'll get the same answer. But some students see it better broken up, some see it better all together. I don't care. Do it whichever way you like, as long as you get the answer. But I haven't answered the question yet. I need to know the edge length of the unit cell and titanium's atomic radius. So if you need to write things down, go ahead and do it now, because I'm going to have to move things and shrink things. Move that there. Okay, so the length is equal, again, to the cubed root of the volume of the cell. So 3.533 times 10 to the minus 23rd centimeters cubed. And I'm going to take the cubed root of that. If you don't know how to do this on your calculator, most of you guys will have to put this in your calculator as 3.533, hit that double E button, minus 23, and then I want you to raise it, it's a little caret symbol, raise to 1 divided by 3. That's how most of you will have to plug this into your calculator to take the cubed root. Go ahead and do this, and you calculate out 3.281, my sig figs are still at that 8, times 10 to the minus 8th, or 328 picometers. This is centimeters here. Now that I have my length, I can go ahead and solve for radius. I know length is equal to 4r over the square root of 3. I'm trying to find r, square root of 3 times my length, divided by 4, square root of 3 times 328 picometer, divided by 4, I get a radius of 142 picometer. So my two answers here, 328 picometer for my length and 142 picometer for my radius. Okay, what about this one? The radius of gold is 144 picometer, and density of gold is 19.32 grams per centimeter cubed. Does elemental gold have an FCC structure or a BCC structure? Honestly, I've got to calculate it both ways and compare it to the actual density of gold. I don't know the answer. So I'm going to just calculate it both ways. First, I'm going to calculate if it's FCC, just because FCC is listed first. I don't care which one you do first. FCC, remember FCC, we have 1/2 times 6 faces, 1/8 times 8 corners, so 4 atoms per cell. Find the mass of your cell. If I look up gold, 196.97 grams of gold are contained in 1 mole of gold. I know 1 mole of gold contains 6.022 times 10 to the 23rd gold atoms. And I know there's 4 atoms per cell because it's FCC, or that's what I'm checking first. 1.308 times 10 to the minus second grams per cell. I need the volume, and for FCC, the length is equal to 4r over the square root of 2 but volume is cubed of that. So 4R divided by the square root of 2 cubed is my volume. I have 144 picometer. I need to get that into centimeters though, because I'm going to compare the density as centimeter cubed, so I really need this in centimeters. 144 picometers. A lot of you guys have forgotten this one. 1 picometer is 10 to the negative 12 meters, or you could say 10 to the 12th picometer is 1 meter. Picometer is really, really small, so it's like 10 to the 12th picometer to 1 meter, or 1 picometer is 10 to the negative 12th meter. Convert that to centimeters. I know 100 centimeters is 1 meter. So 1.44 times 10 to the minus 8th centimeters, and this is equal to R, because it's your radius. So I've got 4 times 1.44 times 10 to the minus 8th divided by the square root of 2. Quantity cubed gives me 6.757 times 10 to the minus 23rd centimeters cubed per cell. Now I'm going to calculate the density. I'm going to do that up here. 1.308 times 10 to the minus, that should definitely say 21 there. So please make sure you wrote 21, not 10. I think I cut it off earlier when I erased something by accident. 10 to the minus 21 grams per cell divided by 6.757. Underline that 5 where my sig figs are at. Times 10 to the minus 23rd centimeters cubed per cell. My density equals 19.4 grams per centimeter cubed. It's really, really close. I'm going to erase some of this so I can write some other stuff, so please pause and write down if you need to. But if I was to calculate this for BCC, BCC is 2 atoms per cell. So everything stays the same except the calculation here. I would get 6.542 times 10 to the minus 22nd grams per cell. And the density would be 9.68. So he's writing times 10 to the grams per centimeter cubed. So therefore, gold is FCC, because we found that the density, 19.4 and 19.32, basically the same thing. We had to round when I calculated your volume based on your radius. And that matches the density of gold. If it was body-centered, it would have a density of 9.68 grams per centimeter cubed, which is not correct for the known density of gold. How can we figure out the known density of gold? Displacement reaction. Go take a sample of gold, weigh it, put it in water, figure out how much volume it displaces. We find the volume of that sample and calculate mass over volume to find the density of gold. Manganese, Mn, is a body-centered cubic. So again, body-centered, BCC, 2 atoms per cell. Has a density of 7.88 grams per centimeter cubed. From this information, determine the length of the edge of the cubic cell. So again, BCC, 1 body, plus 1/8 times 8 corners, 2 atoms per cell. The mass of the cell I've got 54.91 grams for manganese per 1 mole of manganese. I know 1 mole of manganese contains 6.022 times 10 to the 23rd manganese atoms. That is a 2 there. I know I have 2 atoms per cell. So I got 1.823 times 10 to the negative 22nd grams per atom of manganese. It tells me the density is 7.88 grams per centimeter cubed. So I know that 1 centimeter cubed weighs 7.88 grams. Multiply this by 1.823 times 10 to the minus 22nd grams per atom. It's just like dividing it by the density. Kind of same thing, just showing it in showing it in dimensional analysis, not just the calculation. This gives me 2.314 times 10 to the minus 23rd centimeters cubed per atom, which is your volume. My edge is going to be the cubed root of that, 2.314 times 10 to the minus 23rd centimeters cubed. Take the cube root of that. This gives me 2.85 times 10 to the minus 8th centimeters, which I'm going to convert to 285 picometer because we just don't really like really small numbers. So 285 picometer. You'll also sometimes see me write this as angstrom, 2.85 angstrom. An angstrom, I don't even know how to spell it. I think it's that. I'm not positive. Angstrom is just 10 to the 10th angstroms is equal to 1 meter. It's a little a with a little dot over the top. But it's just 10 to the negative, 10 to the 10th angstroms or 10 to the negative 10th meter to 1 angstrom. And you'll often see us measure it in this unit because it just makes sense. 2.85 angstroms makes sense. We measure a lot of bond lengths and stuff in this unit specifically. If the unit cell of sodium chloride is 5.56 angstroms, I don't know why, but on this one I completely forgot to mention that NaCl is FCC, which means 4 atoms per cell. What is the density of sodium chloride? So I want the mass of a unit cell. I know sodium is 58.44 grams per mole. I know that there's 1 mole for every 6.022 times 10 to the 23rd formula units. And I know that I have 4 formula units or atoms per cell. I didn't actually calculate this. What did I write down? I don't know where my calculator is either, so I can't write that down right now. What I actually did was just calculate it slightly differently. I wrote the mass, I'll get you the right answer in a sec, but the way I wrote this out was mass of unit cell. I do apologize too, I don't know where I set my calculator. I just said 4 times 22.99 AMU for the 4 sodiums in the unit cell, plus 4 times 35.5 AMU for the 4 in the unit cell is 234 AMU, atomic mass unit. I want the density. I know 234.0 AMU is the same as grams per 1 mole. I know that 1 mole is 6.022 times 10 to the 23rd NaCl, formula units. And I know that the volume is 5.56 angstroms cubed. And I know that 1 angstrom, I will explain these things in just a sec. I know 1 angstrom is 10 to the minus 8th centimeters, which gave me my answer of 2.26 grams per centimeter cubed. I wrote it all out in one fell swoop. Now let me explain a couple pieces to it. This, just like we've done before. This, in angstrom, again, 1 angstrom is 10 to the minus 10th meters, or 10 to the 10th angstroms is 1 meter. An angstrom is just a really small unit of length. It's just between, like, micro is minus 6, pico is minus 12, angstrom is just minus 10. Tells me it's this on an edge. Edge is your length. So it gave me the distance of a length. Because angstroms are 10 to the minus 10th, I could do this a couple different ways, but let's just say 1 angstrom, convert that to meters. Convert that to centimeters. I know 1 angstrom is 10 to the minus 8th centimeters, which is what I put there. So I took some liberty and shortcuts here. And I don't have my calculator to write out the shorter, longer forms for you guys. So I hope that makes sense to you guys. But basically finding the density. I still found here the mass of the unit cell. I divided it by the volume of the unit cell. And then I was given the original volume, or the original length in angstrom, so I just had to convert to centimeters to get centimeters cubed for the density. Which of the 4 basic types of solids would you expect the following substances to be? A, solid ammonia. Ammonia, NH3. If ammonia was in a crystal structure, let's think about what ammonia looks like. Ammonia, I know, follows this pattern. Its electron geometry is tetrahedral. Its molecular geometry, trigonal pyramidal. I know it undergoes hydrogen bonding, so therefore it's got LDF, dipole, dipole, and hydrogen bonding. But I also know it is molecular. B, cesium. Find cesium on the table. You're going to find cesium down in your lanthanides or actinides series. It's in your F block. I don't remember which roads, and I think it's in your lanthanides. I don't remember for sure. But it is a metal. So you're going to expect this to undergo metallic. Cesium iodide. I've got a metal and a non-metal here. I expect this to follow ionic. And D, silicon. We talked about silicon and its extended networks. We expect this to follow a covalent network. Okay, here is one of the challenge problems that I pulled from one of the textbooks. But you guys can do this. X-ray diffraction from crystals provides one of the most accurate ways of determining Avogadro's number. Silver crystallizes in a face-center cubic lattice with all atoms at the lattice points. Remember, face-center cubic means 4 atoms per cell. The length of an edge of the unit cell was determined by X-ray diffraction to be 408.6 picometer or 4.086 angstroms. The density of silver is 10.5 grams per centimeter cubed. Calculate the mass of a silver ion or silver atom. Then, using the known value of the atomic weight, calculate Avogadro's number. So we know volume is equal to L cubed, or your length cubed. It tells us that the length is 408.6 picometer or 4.086 angstroms. That is the same as 4.086 times 10 to the minus 10th meters cubed. If you need to do the conversion, do it on your own, that's fine. but picometer is minus 12, angstrom is minus 10. So 4.086 times 10 to the minus 10th meters cubed is the volume, which equals 6.822 times 10 to the minus 29th meters cubed. Density, 10.50 grams per 1 centimeter cubed. I know there's 100 centimeters in 1 meter, but I have to cube that because I'm trying to cancel out my centimeters cubed here because I want to get my density in grams per meter cubed because I want to find the mass of that atom. So this cancels this out for me. This gives me 1.050 times 10 to the 7th grams per meter cubed. If I had an entire meter cubed of this stuff, that'd be like a box that's 1 meter by 1 meter by 1 meter. It would weigh 1.05 times 10 to the 7th grams. It's a lot bigger box than 1 centimeter by 1 centimeter by 1 centimeter. I know mass is equal to density times volume. Because again, remember density, mass over volume. So if I want to solve for mass, I'm going to get density times volume. 1.050 times 10 to the 7th grams per meter cubed times the volume, 6.822 times 10 to the minus 29th meter cubed. Cancels out my meters cubed, gets me grams. This shows me 7.163 times 10 to the minus 22nd grams. So I know that FCC, again, is 4 atoms per cell. One atom at each lattice point. Is what the question tells me. So I don't have any holes, nothing's missing. The mass of one silver atom would be 1/4 the mass of the unit cell, because this is grams of my cell. The mass of one silver atom, 1.791 times 10 to the 22nd grams. I know that the atomic weight of silver is 107.87 AMU, which means the molar mass is 107.87 grams per mole. So Avogadro's number, 107.87 grams per mole, divided by 1.791 times 10 to the 22nd grams gives me 6.022 times 10 to the 23rd per mole. And you just confirmed Avogadro's number. Platinum crystallizes in a face-centered cubic lattice with all atoms at the lattice points, FCC. So 4 atoms per cell. Has a density of 21.45 grams per centimeter cubed. An atomic weight of 190.08 AMU, but I can get off the periodic table as well. Calculate the length of a unit cell edge. How does this compare to the literature value of 392.4 picometer? So I've got 195.05 or 08 AMU, density 21.45 grams per centimeter cubed. I've got a literature value I'm comparing it to. I'm going to calculate the mass of the atom. So mass of a unit cell. From the atomic weight. I know density. And if I know that and mass of unit cell, I can find volume, which will lead me to L, which is edge length. So 195.08 grams of platinum to 1 mole of platinum. I know 1 mole of platinum contains 6.022 times 10 to the 23rd platinum atoms. I know it's FCC, so there's 4 atoms per unit cell, which gives me 1.296 times 10 to the minus 21st grams per unit cell. I know my volume. I can take my mass divided by my density. I've got 1.296 times 10 to the minus 21st grams in that cell. And I'm told the density is 21.45 grams per centimeter cubed. This gives me 6.042 times 10 to the minus 23rd centimeter cubed. But this is volume, so this is equal to L cubed. Take the cube root of L, or cube root of V to find L. So 6.042 times 10 to the negative 23rd centimeters cubed. I'm going to take the cube root of that. This gives me 3.924 times 10 to the minus 8th centimeters, which I can say 392.4 picometer, 3.924 times 10 to the minus 10th meters, angstrom, etc. But how does that compare? Perfect, right? You guys just confirmed the literature value of the edge length of a platinum atom specifically. Let's see. Classify each of the following solid elements as molecular, metallic, ionic, or covalent network. Tin. It is a metal. It is metallic. Germanium. This one might be a little confusing. Germanium is actually one of your metalloids. This undergoes a covalent network. It's like diamond. Sulfur. Sulfur really likes to be S8. It is molecular. Iodine, one of your diatomics, also molecular. Number 9, associate each type of solid in the left-handed column with 2 of the properties in the right-hand column. Each property may be used more than once. Molecular solids. Molecular solids are low melting. They're also brittle. Ionic solids, high melting. They're hard, but they're often brittle. Metallic solids, malleable. They're electrically conducting. Covalent networks, they tend to be hard. They tend to be high melting. So just thinking about some of the different properties these things have. Number 10, how many atoms are there in a simple cubic unit cell of an atomic crystal in which all atoms are at the lattice point? Let's think about what this means. Draw a simple cubic. in simple cubic. 1, 2, 3, 4, 5, 6, 7, and 8. That's your simple cubic. How many atoms are there? Each atom, there's 8 corners. But each corner is shared by 8 cells. So 1/8 times 8, 1. There's 1 unit cell in a simple cubic structure. That's all that question's asking. When it says at each lattice point, it means your points that the atoms actually, or the atoms will be at in the crystal structure for simple cubic. And scrolling too fast. Okay. Metallic iron has a body-centered cubic lattice with all atoms at lattice points and a unit cell whose edge length is 286.6 picometer. The density of iron is 7.87 grams per centimeter cubed. What is the mass of an iron atom? Metallic iron, body-centered cubic, so BCC, so 2 atoms per cell. Edge length 286.6 picometer, and density is given. And I want to know mass of an iron atom. So I've got, I'm going to write up here because I've got a little bit to write. So 286.6 picometer. I'm going to convert that to meters. .866 times 10 to the minus 10th meters. If I calculate the volume, that's giving me the edge length. So the volume is 2.866 times 10 to the minus 10th meters. Keep hitting the screen, sorry. Cubed gives me 2.354 times 10 to the minus 29th meters cubed. I know that my density is 7.87 grams per 1 centimeter cubed. I'm going to go ahead and convert that to meters cubed just to keep consistent with what I have above. You could have also converted picometers straight to centimeters. I don't really care which way you do it, as long as your math is correct. Gives me 7.87 times 10 to the 6 grams per meter cubed. Mass of 1 cell. I've got 7.87 times 10 to the 6 grams per 1 meter cubed times the volume, 2.354 times 10 to the minus 29th meters cubed. Gives me 1.85 times 10 to the minus 22nd grams per cell. It tells me iron is BCC, so I know there's 2 atoms per cell. So 1.85 times 10 to the minus 22nd grams per cell times 1/2 atoms per cell. I'm trying to write 1 cell per 2 atoms is what I'm trying to write. So I'm dividing by 2 because it's 2 atoms per cell, 1 cell per 2 atoms. 9.26 times 10 to the minus 23rd grams per atom. Check this by using your answer. So this is telling me that I've got 9.26 times 10 to the negative 23rd grams per atom, okay? What I want to do, though, is check my answer. By calculating the mass of 1 iron atom. That is the word of. I know iron is 55.85 grams per 1 mole. I know 1 mole, 6.022 times 10 to the 23rd, 9.27 times 10 to the minus 23rd grams per iron atom. Answers are in agreement. Now, some people may say, why did you make me do all the work? I could just do it the short way. Because it's practice. That's just the flat out answer. I gave you extra information, and it's just practice. And our last example. Gold has cubic crystals whose unit cell has an edge length of 407.9 picometer. The density of the metal is 19.3 grams per centimeter cubed. What is the number of gold atoms in a unit cell, assuming all atoms are a lattice point, and what type of crystal or cubic lattice does gold have? Okay, so let's see. We know our edge length is 407.9 picometer. We know density is 19.3 centimeters. We also know it's cubic. So I'm going to find the volume. Volume is equal to my edge length cubed. So 407.9 picometer is the same as 4.079 times 10 to the 8 minus 8 centimeters. You guys can do that calculation if you'd like to check it. But I want to put this in centimeters cubed because I'm going to have to compare it to density, and I want my units to be the same. 4.079 times 10 to the minus 8th centimeters, quantity cubed, gives me 6.787 times 10 to the minus 23rd centimeters cubed. Now I'm going to take my density, 19.3 centimeters cubed, 19.3 grams per 1 centimeter cubed. That looks better. And multiply it by my volume to get the mass of my cell. 6.787 times 10 to the minus 23rd centimeters cubed. It gives me 1.3098. The 9 is where my sig figs are. I just don't want to round yet. Times 10 to the minus 21st grams per cell. Now I'm going to kind of do the math backwards from what we've done before. I'm going to say, okay, I know that I have 1.3098 times 10 to the minus 21 grams per 1 cell. I know that 1 mole of gold weighs 196.96 grams. And I know that there's 6.022 times 10 to the 23rd gold atoms per 1 mole of gold. So that cancels out my moles of gold, my grams, and that tells me my atoms per cell, which tells me 4. If I calculate that, I'm going to get 4 atoms per cell. It tells me gold is cubic. If I have 4 atoms per cell, I've got an FCC, or face-centered cubic structure.